Hello, dear students. Welcome to the new series of lectures that I'm going to discuss are these complex analysis. And now today's topic is because if you remember that, so our main focus is on only on the problems, on the different topics that we choose in a complex series, complex analysis. And now today's topic is about that's basically Taylor expansion, right? So this one of the application of that Cauchy integral theorem is that so we can use it to expand a series of functions in this complex plane, right? So this is one of the application so by which we can solve some complex function, so we can construct that Taylor series expansion. So you might be familiar with the Taylor expansion in your during your graduation, so so you know how to expand that series. And today we are going to discuss one of the applications, so how we can with the help of that Cauchy integral theorem, so how we can construct that Taylor series expansion, right? So first let's because we are talking about these complex plane. So first, if we consider that we consider some point here that is basically z point. So we are considering here some z point which is nearest point to this. So that means we have some point, we have some domain D in a closed loop. So this is our closed loop here, okay? And we have some point on that closed loop that is Z1, right? And we choose some point Z0. So while we suppose that the function is not analytic, right? So there may be there may be more than one functions where the function cannot be analytic, right? So this is one of the point where we say that the function is not analytic, right? And similarly, if we choose another loop within this domain, so because if you talk about that, so you have this z minus z naught. So this simply gives us that if you put that z minus z naught, so that is z prime minus z naught. So that's our small r. That basically gives us the radius of that closed circle. And similarly, if you take that z1 minus z naught, that gives us the this radius of the big circle, right? And it's very clear from here that we can write that z prime minus z will be equal to z1 minus z naught, right? So that means the series will converge within this domain, right? So series will converge here. Now, so from the statement, so with the help of, so after doing this, all these derivations, so with the help of this Cauchy integral theorem, so we can prove that f of z, f of this z will be equal to, so that is summation n starts from 0 to infinity, that z minus z naught raised for n, and fn of this. So that means, so we are basically writing that, so it n takes the different values of this, so that means if you put that n equal to 1, 2, and 3, so that corresponds to our first, second, or third order derivatives. Now, coming back to also, I'm saying that so how we calculate this? So first we are saying that this is basically that so all the points within this domain. So you can have some points where the function can be analytic and some where the function or this f of z cannot be analytic at that point. So one was z0. So I am choosing one more point that is nearest to the z prime. So this z is so it is the function is not analytic at that point. So then again, so with the help of, so if you remember that with the help of the Cauchy integral term, so we can write that f of z as that 1 by 2 pi I, that integral f of z dz divided by z minus z naught raised by n plus 1, right? So after doing this all these derivations, so you can prove that the f of z will be equal to this. Or you can put the different values of this n, so from 0 to infinity. So we can write that this f of z will be equal to this, because putting that n equal to 0, 1, 2, 3 corresponds to this series, and this is r minus r naught, right? So z naught is, so if you remember that this z naught is our, that's basically the center of this closed loop, right? Either you take that inner or outside the loop, so it is that one. Okay. Now, so we will use this now. So because so we'll see that with the help of this result. So you can use this result, or you can use this result also. So one of them. So we can develop now the Taylor series expansion of some of the trigonometric functions, or take some exponential function, or some series you can take in. So you can construct that expansion, Taylor series expansion, with the help of this Cauchy integral term, right? So first let's take an example here. So we'll take this example that you need to develop that Taylor-Series expansion for the function of f of z equal to 1 by z at z equal to 2, right? So we need to develop this Taylor-Series expansion for this. So first, so you know that, so we can write that f of z will be equal to. So you can write that. Okay, so this first function, and similarly, okay. So let's put all these values here. So first we calculate the derivative of this function, like we have this f of z. So we calculate its derivative. So different derivatives, and we substitute it here, and the point where our function is not analytic, so that's z0 here, right? Okay. That's given in terms of that f of z. So z is also that point where the function is not analytic, right? So you can write now, so you put that where f of z is, that's equal to 1 by z, right? If you calculate now, or you put it here like, okay, so similarly you can go the to calculate the derivative for the of the nth value, right? So first you just we can develop this series. So we can write in some, because it follows some pattern here. We can write that, because you need to put that f of z, that's at z equal to, right? So you write this will be equal to. So you can write this as at z0 equal to. So this will be equal to 1 by 2, and this will be equal to minus 1 by 2. Okay. So you can write it here. Okay. So I think it's clear. So first, by putting that f of z at z equal to 2, so giving the different values here, and I can rearrange it like this, because we have this minus 1 by 4, you can put it some minus 1 raised power 1, 1 by 2 square. And similarly, you have the plus, so you can put that minus 1 raised power 2, right? So it gives us plus value, right? And this is 2 factorial divided by 2 cube, because we have 8 here, so this 2 cube. And similarly, that's minus 6 by 16, you can put that minus 1 raised power 3, and so on. So that means it basically follows the kind of pattern here, right? So that means I can generalize it, I can put for the nth values. So you can write it as, so if you calculate now fn of z, so that will be equal to minus 1 raised power n, and factorial 2 raised power n plus 1. Why? Because when you calculate the third derivative here, so you can put it like this. That's minus 1 cube can put it like this. So it follows a series of patterns. So that means the function fn of this z will be minus 1 raised for n factorial divided by 2 raised for n plus 1. So that means I can rewrite this series as, so this will be equal to that f of z minus 1 raised for n, and it is that minus 2 raised for n. Okay, so just check. So my previous slide here, so this is, you are getting that fn, but we have, when we write that Taylor series expansion, just go back to our this result. So why is that? Okay, or it is this way, or you can put it like this. So that means z minus z0, right? So our z0 is for 2, so that's why I put that z minus 2 is for n, and we have this fn of z0 that's equal to, so we can put that value. So this is what I how I can write it, because we have this minus z minus z0, so z0 is our 2, so z minus 2 raised for n, and similarly minus 1 raised for n, 2 raised for n plus 1. So this is how you can construct this Taylor series expansion with the help of Cauchy integral that theorem. Now, if I take one more example, one of the most common example you might be familiar with that example. If you take the expansion of some sine functions or cosine functions, right? So with the help of that Cauchy integral theorem, so let's do that. So we should get some expansion if we use so we know that the expansion of that sine and cosine function is, if you take that sine function, we have that sine of x, that's x minus x cubed by 3 factorial plus x raised for 5 by 5 factorial minus x raised power 7 by 7 factorial and so on. Right? So that means we can well, let's construct that this Taylor series expansion for sine term, right? Okay. So let's write that. So I will take one more example. Okay, let's write it here. So we need to use the Taylor series expansion. Use Taylor series expansion for sine z at so that means we need to construct the Taylor series expansion at z0 equal to 0. Right? So that means our point where the function is our, where the function is not analytic, so that's our z0 equal to 0. That's the origin of the complex plane. Right? So you are taking that at origin of that complex plane. So you need to develop that Taylor series expansion. So using that Cauchy integral theorem. Right? So first let's write that. Okay, let me write here. So first we know that our Taylor series expansion. So you know that, so that f of z is, that is f of z0 plus f dash of z0. Okay. So this, so that how we can express this function, or you can write it in some general form. So what we have discussed in previous problem. So let us expand this. So our function is here. So f of z is, that is sine of z, right? Or you take that, what's our f dash of z? So that's cos z, and f double dash of z, that is minus sine. And similarly, so we have calculated the second derivative. Similarly, you can write that. Okay. So what I have done here, so I simply calculate that we have this f of z is that sine z, f dash of z that's cos of z, and similarly you calculate the second derivative or third derivative and so on, right? So let us use these in our that this initial expression that we have. So and putting that our z0 equal to 0, right? So that means our function is basically f of z. So you need to put that at z equal to z0 equal to 0 here, right? So putting that value and use these derivatives in this expression, so we'll get the Taylor series expansion, right? Okay. So let's use here. So we have this f of z. So that's sine z. So what's f of 0 here? Okay. So first term is 0 because our z0 is 0, right? So you're getting that f of 0 equal to 0, right? And similarly, or f dash of z. So that's cos of z. So f dash of 0. So that's what. F double dash of z. Okay. So let's use it. We have to use these values in this expression because we calculate that f of z0 and similarly we calculate that f dash of z0 and the second and the third derivative, right? So let's use it in this expression and remember one more thing that our z0 equal to 0. So it will be simply that z minus 0 and similarly it will be z minus 0 whole square, right? And so on, right? So let's use it. So f of z will be equal to, because first expression is that is f of 0, so that means z0 equal to 0 because our function is that is sine of z, so z equal to 0, so you can put sine 0 equal to 0. So first term will be 0 plus, and the second term, so that is f dash of 0, right? So f dash of 0 equal to 1 into z minus 0 divided by 1. Okay, so this is our second expression, and similarly for we can have another term that is f double dash of 0, so that's our 0 value and z minus 0 square. Okay. Similarly, if you calculate now, what's our now? Calculate now the third derivative at z, so that's equal to minus 1. So this will be plus into minus 1 and so on. Okay. So if you check here, so first term is 0, so I will get here that is, so first that is z, then so this term is 0, so only odd terms will exist here. So that is this minus z cube by 3 factorial. Okay. And similarly, another term will be that will be plus term. So that will be plus z raised power 5 by 5 factorial. But this series, you get this series only when you put that, when you calculate at z0 equal to 0, this Taylor series expansion. If you calculate at z0 equal to 1 or 2, so you will not get this expansion, right? So similarly, you can do for this if you have cosine term, so you you can find that you can this with the help of this Cauchy integral term, you can prove that this you can also expand this cosine term and get this Taylor series expansion, right? So these were some of the examples that I mentioned here, and similarly I can give you one more problem. So you can also work out for this also. If we have a logarithm of some log of 1 by z, log of 1 by 1 plus z at z equal to 0, right? So remember that every function that we are like we have logarithm function or exponential function. So you can calculate at near at z0 equal to 0, right? So at z0 equal to 0, you can get those Taylor series expansion for these functions. Like if you take some trigonometric function like sine or cosine term, and similar if you talk about these exponential or logarithm terms, so you get the same expansion what we expect from this Taylor series, right? So, but except that you should put that or this where the function is not analytic, so that should be 0. So that 0 z0 will be equal to 0. Okay, I will give one more example. So if you want to expand this, okay, so you write that evolving ln of 1 plus z around z0 equal to 0. Okay, or z equal to 0 you can say. So you need to expand it there. So first, so I will not write this all this expansion of what we have done in previous two problems. So I will write directly that calculate their derivative and substitute in that expression, right? So if I write now, so let's write, so f of z is, so if you calculate now, what is ln of, okay, sorry, so you write this way. Okay, okay. So let us check if we get some kind of pattern here. So we can put it like we can write here. So this will be some minus 1 raised power some. You can put minus 1 raised power n plus 1 here, right? So let us, okay, let's write it this way. So we can put it like this. So we can have this. Uh, we can write it as, so our f of z will be equal to, that is summation n starts from 0 to infinity, and you write that by n factorial, and inside will be, so just check, so our series, so you are getting first will be 0 and second is 1, so it is 1 minus 1 plus 2 and so on, right? So you can write this way, so you can put it like so we can write this as that n minus 1, n minus 1 Right? Because when you put that n equal to 0, so this will be 0. So this will be z raised power 0, that's 1. So first term 1 bit ban jayegi. Then if you put n equal to 1, so that means z1 raised. So you can write this as, sorry. So because we have this, so we can write this way. Minus 1 raised power n, minus 1 raised power n divided by n factorial. Okay. Because we have this, because when you put that n equal to 0, 1, 2, 3, you will get that all these terms, because our terms are these. So you just check. So we have this 1. So first is 0, second is 1, third is minus 1, then it is 2. So you can rewrite this as summation and starts from 0 to infinity. That is n minus 1, that is for n upon n. Okay. Or you can write this as, you can rewrite this as this way. So summation, because we have this, you can rewrite this as n0, 0 to infinity, minus 1 raised power n plus 1, z raised power n, divided by n, right? Because this was n minus 1 factorial here, right? So this was n minus 1 factorial here. So then you can write this as this. Right? So this is how you can expand this. So how you are expanding these functions with the help of these Cauchy integrals, right? So in our coming lectures, we'll talk about that. If we talk about that Laurent series, right? So we'll take that first. I will give you a little bit a bit idea about what are basically Laurent series, how we can construct the Laurent series with the help of that Cauchy integral theorem, and do some problems on these topics that are most probably asked in some competitive exams, right? So hopefully this lecture is useful for you. Thank you.